Okay, awesome. So thank you so much, everybody, for joining us today. In Vancouver, we were just discussing that it's sunny and snowy at the same time. It's kind of beautiful. It's like blue sky. And yeah, so for everybody who has joined us before, so you know that this WESTalk is joined between IC Impact and Future Water. And I'm sure you know that IC Impact by now, that it's a pan-Canadian Canada-India Research Center of Excellence, and UBC Future Water, which is a UBC Research Excellence cluster on the future state of water. And this is the list of the organizing committee: Abhishek, Fuhar, Kar, Firia, Kelsey, and Jaskaran. Abhishek, Fuhan, Carl, and myself are from UBC. Jaskaran joins us from University of Guelph. Kelsey is from University of Victoria, and Firia is the coordinator that helps us with IC. And if you haven't already logged into this Padlet that Carl actually created for us, it shows that or global outreach to people that they attended, or audience from all over the world, which is kind of interesting. And it's something that we actually very proud to be reaching, like all over the world with such a little cause. And this is the lineup today for until like start of January 13 until June 2nd. And after that, it's the BEST conference. And today we are having Dr. Jeseth Delgado Vela. Is that the right pronunciation? I should have asked. And the topic is how I learned to stop worrying and love the biofilm, which is one of my favorite topics, basically. And if you haven't so far attend any of the West talks or WESTalk webinars, and you're interested, you can find the webinars in our channel in YouTube. And with that, I would like to introduce today's speaker. Dr. Delgado Vela is an assistant prof in the Civil and Environmental Engineering Department at Howard University. Her research applies tools in molecular biology to develop sustainable and cost-efficient urban water treatment. She's interested in understanding microbial community interaction to improve the urban water cycle. She received her PhD and master's degree from the University of Michigan and her bachelor degree in civil engineering from the University of Texas at Austin in 2012. She's the recipient of Ford Foundation Dissertation Award and an NSF Graduate Research Fellowship. And with that, I would like to hand it to Dr. Delgado Vela. And if you have any question, please put it in the chat box, and Carl will get them after the presentation. I'll stop sharing.
All right, thank you. Okay, well, first off, thank you for the invitation. I was just commenting on what a great lineup of speakers you have, and so it's nice to be among these amazing researchers. Indeed, my research and my interest have really focused on biofilms. So I'm really excited to be here and talk about my work. Essentially, biofilms are really complex. They can wreak havoc, but they also are just fascinating to study. And hopefully by the end of this, you can understand kind of why they're so complicated to evaluate and understand, but also potential benefits to biofilms within the urban water cycle. So what do I mean when I talk about the urban water cycle? I know this is very familiar to this audience, but traditionally the way we treat or teach and think about water is we think about the drinking water treatment plant going to our homes and places of businesses. And then from our homes, we think about the water resource recovery facilities or the wastewater treatment plants, protecting the environment. But increasingly, we're starting to think about this as one system. So you guys have probably heard the idea of one water, because we essentially need to, there are increased different stressors on the system. And so we need to consider the entire integration of the system. So for example, due to water scarcity, there's increased water reuse happening, both de facto, meaning just that wastewater doesn't spend very long in the environment before it becomes drinking water. And there are also increased instances of engineered direct potable water reuse. But because of this, we really need to start thinking about kind of the health risks associated with what we're emitting from the water resource recovery facility. So this includes emerging pathogens, chemical contaminants, and other potential health risks. I know you guys have on your lineup the idea of health monitoring from the water resource recovery facility. And so I did want to kind of shout this out as something that's really emerged very quickly during this pandemic and will probably be here to stay with respect to how we think about this system. Something else that we're starting to think about more are resources that we might be able to recover from the system. So nutrient recovery, energy recovery, and this water reuse is a form of resource recovery, right? We're recovering water as a resource. So there's both the, at the system scale, some opportunities for water reuse, but there's also kind of more distributed water reuse opportunities with kind of distributed gray water treatment in your homes or places of business or in apartment complexes, et cetera. So in order to kind of improve the sustainability of the system, we're now thinking about this system as far as what type of resources can we extract from the system. But we haven't always been thinking about water resource recovery facilities as resource recovery facilities. Traditionally, when we think about wastewater treatment, we have thought about taking water with contaminants through some treatment process to protect the environment. And that treatment process has some environmental impact associated with it. And traditionally, when wastewater treatment started, we were really focused on carbon removal. As we learn more about the impact that water has on the environment, we've expanded these systems and expanded our goals to include nitrogen and phosphorus removal. We've also thought about, as I said, new uses for the water. So agricultural reuse or direct potable water reuse. But doing so, having these new goals has really expanded the footprint of our system and increased the environmental impact of treatment. And so with our current aging infrastructure, there's an opportunity to see if we can achieve the same ends and the same overall treatment outcomes, but with a lower footprint. And I have come to believe that biofilm treatment systems can really help us achieve this. So traditionally, wastewater treatment is a biological process, right? We're using bacteria to achieve this contaminant removal. So I'm going to talk about two vignettes. So the first one is on a nitrogen and sulfur recycling biofilm, or how I learned to start loving the biofilm. So this is kind of my initiation into the world of biofilms and how complex they can be. And then after that, I'm going to talk a little bit about some of our current work on thinking about whether or not biofilm treatment can enhance system level resiliency. So to start with the nitrogen and sulfur cycling part, I mentioned that, we're increasingly thinking about nitrogen and phosphorus treatment in wastewater systems. And so the reason that we need to think about this is because when nitrogen is emitted into the environment, we create these eutrophic water streams. And so this is an image of the Gulf of Mexico. But across many, many coastal areas, there are many eutrophic or hypoxic regions, and these are caused by nutrient emissions. And in coast, this is primarily due to nitrogen emissions. So if you think about kind of global trends, by 2050, 3/4 of the world's population will be within 200 kilometers of a coast. So this rapid urbanization that we know is happening is also happening while people are moving towards coasts. So we're really going to have to make sure we invest in treating nitrogen moving forward. So how do we treat nitrogen in wastewater? Well, like I said, this is a biological process. So the first step of nitrogen treatment is converting the ammonium that's present in wastewater to either nitrite or nitrate. So the first step is catalyzed by nitrite oxidizing bacteria. In 2015, the nitrification world was forever changed because we discovered Comomox bacteria that take ammonium all the way to nitrate. In a conventional treatment process, we use the organic carbon that's present in wastewater to reduce that nitrite or nitrate to nitrogen gas. So the goal of wastewater nitrogen, biological nitrogen removal is to convert that ammonium to N2 gas. And one of the things that I was interested in studying is the role of sulfide in the system. So sulfide can also be used as an electron donor for denitrification. So it can also be used to reduce that nitrite or nitrate to nitrogen gas. And why is this important? Well, increasingly there are a number of there's growing interest in understanding sulfide and whether or not we can harness it for nutrient removal in wastewater. And most of this interest is actually being spurred by researchers in Hong Kong. So this is because Hong Kong is freshwater limited. So for over 60 years, they've been using seawater for toilet flushing. This has reduced their freshwater demand by 22%. I love talking about this because I think it's an example of the integration of the system. So Hong Kong had a freshwater limitation and they put a solution in place, but that solution of using seawater for toilet flushing has impacted their wastewater treatment plant operation because now they have wastewater that is much more saline, obviously, but also has higher concentrations of sulfur. So they've really spurred some innovations in new technologies to remove nitrogen using this sulfur. And so I understand that the department is quite diverse, so I wanted to go into a little bit about kind of how we treat wastewater and where there might be other sources of sulfur. So as I said, seawater for toilet flushing could be a source of sulfur, but also if you have industrial inputs or seawater intrusion into groundwater sources or into your sewage network, you're going to have higher concentrations of sulfur. So in a conventional treatment system that is focused on carbon removal, you have a biological process, which is where bacteria are growing and converting the carbon to carbon dioxide. And traditionally, you know, sulfide might be rapidly oxidized here, so you won't see a lot of sulfide present in your mainstream, and most of your sulfide will be in the solids handling process. As we expand this footprint to achieve both carbon and nitrogen removal, well, now you're introducing more redox zones where you might have more concentrations of sulfide present. But as I said before, our goal here in general is to achieve wastewater treatment with a smaller footprint and a simpler system. So one of the systems that we were hoping to explore was the idea of using anaerobic treatment for wastewater treatment systems. So in an anaerobic process, you are conducting your carbon removal in this anaerobic digester. You're able to recover energy and you have a smaller footprint system. But you're going to have higher concentrations of hydrogen sulfide. So our interest and the reason why I began to be interested in sulfur was because this was the application area that that we were focused on, is nitrogen removal following an anaerobic process. So in this case, you have high amounts of sulfide that you might be able to harness for nitrogen removal. Ideally, you don't have a lot of organic carbon available, right? Because you've already converted that organic carbon to biogas. You've already recovered that energy. And there are additional metabolisms that we have to consider in this system. So briefly, Anammox is one organism that people have been looking into for denitrification. It uses ammonium and nitrite. And then there are also denitrifying anaerobic methane oxidizers. So these would be of interest in the system because you might have some dissolved methane present that you need to remove. So the biofilm system that we were studying here is called a membrane aerated biofilm reactor. This is a very energy efficient system. They tend to have 4 times better oxygen transfer efficiencies. So you can really reduce the energy demands of wastewater treatment, and there's growing interest in different technology companies in implementing these reactors. So again, we were focused on a membrane aerated biofilm reactor for nitrogen removal after an anaerobic process. And so in this system, the way it works is you have a hollow fiber membrane. So that through that membrane, you're able to supply oxygen. And then you create a biofilm with multiple redox environments. So your ammonium comes into the biofilm, and you can support ammonium oxidizing bacteria and nitrite oxidizing bacteria. So your nitrifiers are growing on the inside of the biofilm. We're feeding synthetic wastewater that had hydrogen sulfide present. So we were hoping to be able to support sulfur-based denitrifiers on the outside of the biofilm. So one of the advantages of this reactor technology for the system is that with membrane aeration, you're basically protecting hydrogen sulfide from being rapidly oxidized or being stripped out of the wastewater. Similarly with methane, right? We're not stripping out the methane, but we're allowing the reactions to occur in the biofilm in this anoxic phase. So this is a pretty unique system that is ideally suited for this type of treatment regime. So I'm going to briefly talk about some of the experiments that we did with this MABR. So we collaborated with researchers at the University of Southern Denmark and the Max Planck Institute for Marine Biology to conduct some rate experiments using 15N. And then we also did long-term stepwise increases in sulfide. So the rate experiments were conducted with and without sulfide, and then we also evaluated the long-term effect of increases in sulfide. So for the rate experiments, we showed that as you increased sulfur concentrations, we saw a decrease in nitrite oxidation rates, but no comparable decreases in ammonium oxidation. And so this is actually exciting and kind of a beneficial outcome of adding sulfide. And the reason that this is because if you think about the nitrogen cycle generally, when you're converting ammonium to nitrate, you have to supply oxygen, and that oxygen is directly translates to energy demands. On the other hand, when you are reducing nitrate to nitrogen gas, you need to supply electron donor. Oftentimes, wastewater treatment systems end up adding chemicals to be that electron donor. And so if you're able to stop nitrification at nitrate, you can reduce both the oxygen demands and the electron donor. And so this result that just a little bit of hydrogen sulfide can reduce your nitrite oxidation rates is quite exciting, because it seems that over the hydrogen sulfide might help us achieve this more energy efficient treatment process. The other thing we noted is that the addition of hydrogen sulfide actually led to more anammox and more denitrifying anaerobic methane oxidizers. So this is whole community sequencing data that we sequenced, and then we recovered what are called bins, which are basically just assembled genomes of these two organisms. And this is just showing the relative abundance. So over the course of the stepwise increases in hydrogen sulfide, we saw an increase in the relative abundance of both these organisms. So what this indicated to us was that when we add hydrogen sulfide to this membrane aerated biofilm reactor, we knew that we were going to shift the redox of the biofilm. But what we learned is that we can differentially inhibit nitrite oxidizing bacteria and have a little bit of residual nitrite, and that helps support anammox bacteria and helps support the denitrifying anaerobic methane oxidizers. So this was a very exciting result, because it seems that sulfide can help facilitate what is called shortcut nitrogen removal, where you are not oxidizing ammonium all the way to nitrate. Unfortunately, though, kind of to emphasize how ugly and how difficult these systems are to study, we also found that sulfide induced dissimilatory nitrite reduction to ammonium. So what do I mean by that? So this is the process I've been showing this whole time, where hydrogen sulfide is used as an electron donor to reduce nitrite or nitrate to nitrogen gas. But what we found is that we actually saw increased rates of DNRA, where nitrite or nitrate are reduced all the way to ammonium. And this can be done with hydrogen sulfide as the electron donor. This can be done with just normal organic carbon as an electron donor. And then to further complicate this, anammox will conduct this process using organic carbon. And what we found is that this is from the rate experiments. So when we fed 15 labeled nitrite, we measured an increase in 15 labeled ammonium when there was sulfide present. When there was no sulfide present, we did not have any measurable ammonium production. So this indicates that sulfide can induce this process in this biofilm system. And so we looked into our data for the different denitrifiers that were present in the system, and we found that there were a number of different organisms that have the capability for dissimilatory nitrate reduction to ammonium. So to kind of wrap up this vignette, what we found is that when we add sulfide to the system, we shift the redox, and we inhibit nitrifiers altogether. And we also have this phenomenon of increased nitrite production, nitrite rates, relative to the rates at which nitrate is produced. And so that encouraged the growth of these beneficial denitrifying organisms. But the other thing that we found is that there was a rapid recycling of nitrite back to ammonium. And so what this basically induces is this, this cryptic cycle within the biofilm that without these rate experiments, we would have never understood what was happening. But as it turns out, this was happening quite quickly. And so Well, in the end, we weren't able to demonstrate really great treatment with the system. We were able to show that this biofilm community was rapidly changing. So I want to shift and see a little bit quickly. So what the motivation for this work is just the amount of extreme weather events. So this is data from the US showing that in 2021, we had 20 separate weather disasters that cost more than $1 billion. And many of these, as you can see, relate to our water cycling. And if we think about the system in general, there are really different considerations with respect to resiliency. So in drinking water systems, there are multiple barriers of control for disinfection. In the US, following 9/11, there was a lot of investment from the Department of Homeland Security in making our drinking water treatment resilient. And so therefore there's detailed risk assessment and mitigation within drinking water systems. Stormwater has really good characterization of resilience to wet weather. And also in the US, there's been a lot of large-scale investments in stormwater systems recently. But stormwater directly relates to the wastewater system resiliency. So in this system, or in wastewater, your resiliency is going to be affected by your sewer network and whether or not the network is using combined or separate sewers. And so one of our questions are, when we think about kind of these small footprint, efficient technologies that are more sustainable, are there trade-offs with respect to sustainability goals? Or does resiliency and sustainability strengthen one another? So if we think about kind of process intensification as a form of managing sustainability, what I mean by that is increasingly we're thinking about making our systems smaller, so smaller physical footprint, lower energy demands, lower chemical use. And there are a number of examples of this type of process, but a lot of the examples include biofilm processes. And so we're trying to study the resiliency of biofilm processes. So how do we measure and define resiliency? So in a conventional treatment system, you're going to have some amount of performance. So this would be normal operation, and then you will have some system disturbance. So this could be a power outage or an extreme rain event. And that may affect your performance, right? And so we defined resiliency 3 different ways. So one is the maximum performance reduction. So how much is performance affected by the disturbance? Another one is recovery time. How long does it take for performance to recover, sorry. And lastly, we think about time equivalent performance reduction. So this encompasses both your performance reduction and your recovery time. If we think about kind of wastewater treatment, oftentimes our regulations are based on mass loading to the environment. And so that is why the time equivalent performance reduction is really important, because we want to think about kind of how much are we putting out into the environment in a given time. And one of the interesting things is that wastewater treatment plants tend to have various treatment goals, right? And we expect that resiliency might be different for different treatment goals. So for one system disturbance, you might see a increase in effluent suspended solids, but maybe that increase does not correspond to not meeting your regulation. And the same system disturbance might not really show a response with respect to carbon, but then for nitrogen, maybe we would be exceeding our regulatory limits. And so we hypothesize that resilience will vary across different treatment goals. And then the other thing we're interested in understanding is the impact of sequential sequence disturbance. So after a system is perturbed and recovers, does the subsequent disturbance have the same effect, or is there an effect from the history of prior system disturbances that affects the overall process resiliency? So we're talking about biological processes, right? So if you have a system that you're affecting a biological process, you're affecting this microbiome, you could imagine that the system may not recover to the same original state. And sequential disturbances are quite common. So this is showing a kind of an extreme example of a treatment plant from our operators in the city of Houston. So the normal operating flow rates is 3 million gallons per day. And they see really intense peaking factors depending on different storms. But they also have storms that can last multiple days. And it takes a long time for the system to return to its steady state. And this is common across all the country, right? Like we have this similar data on storm events here in DC. So as I said earlier, right, our real questions are how do biofilm systems affect resiliency? And one of our hypotheses is that the biofilm geometry will have different resiliency. So what do I mean by that? Well, you can have what are called co-diffusional biofilms, where you have an inert media and a biofilm growing on an inert media. In this case, your oxygen and your electron donor diffuse into the biofilm in the same direction. Whereas a counter-diffusional biofilm, like the membrane aerated biofilm reactor that I showed earlier, you have your electron acceptor oxygen diffusing in the biofilm in the opposite direction as your electron donor. And one of the things that is critical about the system is that you actually have different locations for sensitive bacteria. So nitrifying bacteria are typically the slower growing organisms. And in a co-diffusional biofilm, you're going to have nitrifiers on the outside, whereas in a counter-diffusional biofilm, you're going to have them on the inside. And so we hypothesize that this differing geometry will lead to differences with respect to process resiliency. So my PhD student, Isaac, is working on a process model, among other things he's working on, to evaluate this question. So what we did is we took a historical storm event from that 3 MGD plant, and we created some simulated pollutographs. So this is showing the simulated TSS concentration for the storm. I should say that we're doing some sampling and building out some, using sensor data and building out some more advanced models to link the flow to the pollutant concentration. This actually ends up being a larger gap in the literature than we expected or anticipated. So one of the things we're working on is linking these two. But as a preliminary analysis, we just compared a baseline storm to a simulated storm that was twice as intense, and use these simulated pollutographs to evaluate 3 different processes: conventional activated sludge, the membrane aerated biofilm reactor, which is this counter-diffusional biofilm, and then the moving bed biofilm reactor, which is a co-diffusional biofilm. And so this was a 3 million gallon per day plant with no TIN limit, but a ammonia limit. So our preliminary analysis shows that with respect to nitrogen, at least, the process configuration matters. So this is showing the 1X storm, and you see that the conventional activated sludge, well, they all have differing baseline treatments, but the conventional activated sludge has a longer recovery time and a higher, longer recovery time with respect to nitrogen. The membrane moving bed biofilm reactor has a really high maximum performance reduction, but it recovers quite quickly. And then the MABR, as it turns out, is kind of somewhere in between. And if you look at the 2x storm, this is magnified even more. And so what this told us is that our hypothesis was somewhat correct, right? But the biological process does impact nitrogen resiliency, and activated sludge systems appear to be less resilient with respect to nitrification. So this is just a preliminary analysis. Our collaborators in Houston are operating pilot scale reactors of both the co-diffusional and the counter-diffusional biofilms, and are doing some challenge tests to evaluate resiliency in this system. So I think with that, I hope that you feel that biofilms are really complicated to understand, but have potential sustainability and process configuration improvements. And I thank you so much for your attention and for inviting me to speak. So I didn't get to talk about all the students I have in their work, but I did talk about Isaac's resiliency project. And so again, thank you so much for your attention.